Hello, welcome to this demonstration of the LC3 Visualization. My name is Brian Armstrong. I'm a professor in the College of Engineering and Applied Science at the University of Wisconsin, Milwaukee. For this video, we're going to start in the most advanced mode, which is called full control mode. In this mode is most suitable for lecture demonstrations. In full control mode, there is no instruction execution. Rather, the computer components, such as multiplexers, decoders, or buses, are directly controlled through the user interface by the mouse and mouse clicks. Full control mode is useful as a lecture tool for explaining the functions of the components that make up a computer. In this mode, I can control all of the components of the LC3. To keep the time reasonable, this demonstration will not be exhaustive, and so if you have questions about how some of the steps are done, please refer to the LC3 Visualization user guide that's available on GitHub, or send an email to any one of the authors. Now, to illustrate, I will activate the Memory Address Register Multiplexer, or MARMUX. When a component is active, it turns bright green. Here, by clicking on the MUX select, I have activated the MARMUX. The simulation knows that when the MUX is active, its selected input is active, which in this case leads to the address adder, leading to the two address adder input multiplexers and to the selected data sources. In the LC3 visualization, activated means that a component is contributing to the processing currently occurring. For example, when the MARMUX is producing an address that will be stored or used, it is highlighted in green along with the data sources that contribute to the result. In full control mode, the LC3 visualization supports demonstrating how the computer's basic components work. The address 2 MUX, for example, has 4 inputs. I'll set a value in the instruction register. I activated register editing with a right click on the register. All processor registers in memory can be edited this way. Now, with data in the instruction register, the 4 paths into the address 2 multiplexer have 4 different data values. I can demonstrate changing the select signal and how that changes the data that passes through the MUX, and how that changes the calculated value. The visualization, used as a lecture demonstration in full control mode, allows me to demonstrate what the multiplexer does. I can activate the gate MARMUX, which pushes the MARMUX value onto the main bus. The full control mode is complete in the sense that all control patterns generated by the timing control unit in the LC3 processor can be set up. It is possible to execute instructions in full control mode, although that takes a lot of clicks. For example, activating the arithmetic logic unit, the source register 1 path has a 3 to 8 decoder driven from a 3-input multiplexer that selects between bits 11 to 9 in the instruction register, 6 to 8, or the constant 6. As a control, I can change the MUX selection bits to select inputs 0, 1, or 2. This changes the decoder input between the 3 values, in this case 1, 0, or 6, and the decoder activates one of 8 register select lines that activates a register. The register pushes data then out the source register 1 data path, which provides an input to the arithmetic logic unit, changing the output of the arithmetic logic unit, which is propagated onto the main bus. If I change the SR1 MUX select, all of the data in the data path changes. The selected register changes, the data changes, the output of the arithmetic logic unit changes, and the data on the data bus changes. The LC3 visualization is built with a conventional graphical user interface approach, with controls, a model, and the viewer. In particular, in the model, each of the components are modeled with their function. The multiplexers multiplex based on their input, decoders decode and activate one select line, the selected register or memory passes its stored data, and so forth. In each state, components that are active are painted in a color. The data path is painted green, memory or register select lines are painted orange, information is painted blue. At this point, I would like to introduce the design philosophy of the LC3 visualization. Just as Pat and Patel take "nothing is magic" as an organizing theme of their textbook, the LC3 visualization was designed with the philosophy "nothing is hidden." This means that this means that everything is there all of the time. A value from the novice student's perspective is that nothing moves and nothing ever disappears. The instructions and the assignments can be simpler. For example, in an assignment that has the student walk up to a specific microstep of a specific instruction, something we'll see in a moment, there is no effort expended on changing views or perspectives to observe the action of interest. The LC3 visualization is visually busy, but it is all there all the time. Partially to assist the novice student through the complexity, in our program at UWM, we use the LC3 visualization throughout the semester. We stay with a highly directed exercise that runs a short program and asks very specific questions. The specific questions focus attention on individual components, such as the main bus, and reduce the necessity of understanding everything present at once. Painting specific components bright green also helps with focus and allows us to direct the student component by component until all components are introduced. And finally, computers are complex. There's no visualization that animates all of the workings of a computer and is not complex. Now let's shift gears and look at program execution. I start by loading a program object file. The LC3 visualization loads object files produced by the LC3 tools, an integrated development environment for the LC3 recently built by Sharig Sakuja at the University of Texas, and based on earlier work by others. As it loads, the LC3 visualization analyzes the object file and paints memory red for program code, blue for the stack, purple for global variables, and orange for constants. Gray shows unused or uninitialized memory. I'll explain the analysis in a moment, but first I would like to introduce the display modes of the LC3 visualization. Values can be shown in hex, signed decimal, unsigned decimal, as decoded instructions, or in ASCII. The control is by mouse click and cycles through the display modes, similar to other controls. I'm going to set a breakpoint done by a left mouse click on the desired location. We are about to run the program in auto step mode, but first I set the step size to run continuously. The program is now running in auto step mode. The visualization incorporates the state of the machine described in Pat and Patel with microsteps introduced. And now a bit on the use of colors to label memory. When an object file is loaded into the LC3 visualization, it is analyzed to identify how words of memory are used. The analysis involves information in the object file, as well as running the program in simulation and analyzing memory use. For example, if a word is fetched into the instruction register, it is labeled as an instruction word. Red is for program memory. And if we click to view words as instructions, only those that are labeled as instructions are decoded. Blue is for the stack. At this point in the program, our subroutine is allocated 4 words on the stack. Purple is for the global variables area. The model of program memory stack frame, and other data follows the C language execution model described in Pat and Patel and used by the LCC compiler. The dots indicate pointers. The red dot indicates the currently executing instruction. The blue dot indicates where the stack pointer is pointing. The purple dot indicates the global variables pointer. And the black dot indicates the current stack frame pointer. Education research indicates that misconceptions about pointers and the use of memory are important barriers to better mastery of introductory computing. The coloring tools are directed towards rendering this otherwise invisible aspect visible. Additional features are control of the step size in auto stepping. For example, I can set the step size to microstep and walk through an instruction one microstep at a time, something every student should do at least once. The visualization captures the LC3 state at the start of each instruction so I can walk back through one or several instructions. When I have backstepped, the forward control takes the state forward, permitting the lecturer to rock back and forth across an instruction, perhaps drawing attention to the multiple actions of some instructions. Register editing allows the student to change the data processed by a program. For example, I can type string data terminating with the enter key. I hope you have enjoyed this video on the LC3 visualization. If you have questions, feel free to contact me at the email address shown.